So now we're going to focus on rational functions that do not have a horizontal asymptote. So remember, how I can tell that they don't have a horizontal asymptote is that I see the higher degree in the numerator of the function. So when I look at this function, I'm going to rewrite it just so that the x is the first term in that denominator. And there's nothing that can be factored or canceled. So that means there are no holes, right? So let's just keep track. So we're always looking for asymptotes. And we just said we're doing the ones with no horizontal asymptote. And then we're looking for intercepts and holes. So when I look at this, since nothing cancels, I know that there are no holes. I know there's not a horizontal asymptote, which means there must be an oblique asymptote. And if you guys remember how we find the oblique asymptote is that we actually do division here. So I'm going to think about this in order to find the oblique asymptote as 5x squared plus 0x plus 0 being divided by x plus 3. And now you can use long division or synthetic division for this one, because remember, synthetic division works with a divisor who only has a first power on x and whose lead coefficient is 1. So I'm actually going to use synthetic division. So -3 would be my number here in this box. My coefficients would be 5, 0, 0. And it is important that you have the 0 placeholders because it will adjust the other numbers. So I dropped down that first 5, and now I'm going to go ahead and finish this. So 5 times 3 is -15, and 3 times -15 is 45. So remember what this means. This means the answer to the division problem is 5x minus 15 with a remainder of 45. However, we talked about for the oblique asymptote essentially being able to ignore the remainder portion. You have to understand mathematically why that's okay. You get to ignore the remainder because end behavior is based on very large numbers. And so when you plug in really big things to this denominator, this fraction almost becomes 0. So it becomes what we call like a negligible idea when we're just trying to see where the function follows. So we're going to focus on this portion as the line that our function's going to follow instead of a horizontal asymptote. So it's going to follow the equation of this line. All right, so in our asymptotes, we determined our oblique, which means there's no horizontal. Nothing canceled out, so there's no holes, but we haven't addressed our vertical asymptote. Remember that vertical asymptotes come where the function is undefined. So where would the denominator be equal to 0? That would occur at x equal to -3. So I have a vertical asymptote at the vertical line of -3, splitting my function into 2 branches. Then we're going to look at the X-intercept and the Y-intercept. So for the X-intercept, we set y equal to 0. And some of you guys might have been seeing a pattern. Essentially, as you guys go to solve these, if you use our procedure of multiplying both sides of the function by the least common denominator, then what's going to happen every time is you're using the denominator that's here on the right side. So on the right side, the denominator gets canceled out and we're only left with the numerator. And on the left side, you're multiplying all of that stuff in the least common denominator times 0, so it remains 0. Then I would divide by 5. And square root, and I get that x is equal to 0. And I think it's important here really to remember that your x-intercept is a point so that you understand you're plotting that on the graph. And so again here, you kind of see that every time you end up with that numerator equal to 0. And then lastly, let's talk about the y-intercept. For the y-intercept, we're plugging 0 in for x. Because of the way we write our functions, that should mean we just have to do some arithmetic to figure out the y-intercept, which again, we get 0. So what this means I have on my graph, I'm going to mark everything that's here. I have a vertical asymptote at x equals -3. I have an oblique asymptote at y equals 5x minus 15. So Actually, I'll keep this. So notice that I have to graph this line that has like a slope of 5 and a y-intercept of negative 15. That's really big for my graph. So I'm actually going to number the y-axis by 5s. And so then that will make the y-intercept of 15 sit right here. Negative 15 will sit right here. And then a slope of 5 would be up 5 over 1. Since I'm numbering my y-axis by 5s but my x-axis by 1s, it gives me this line. But you have to make sure you understand the scale. So this will help a little bit so that I don't have to make a giant graph. So I have this here. And now I'm going to plot some points that actually belong on my graph. There's no hole to plot, and the x and y intercept are the same. And now I got to figure out what's happening. So I just want to remind you guys that number one, you know that you have one branch of the graph on this side of the asymptote and another branch on this side, that this asymptote at x equals negative 3 is splitting it up into two parts of the graph. So we definitely have to decide two different things that are happening there, and that's split up by negative 3. So we are going to do that sine analysis. And so one thing that we're looking at is that negative 3 on the x-axis is what's splitting it into the two branches, and we need to see what's going on both sides. The second thing I want to remind you of is that a graph can also cross through the x-axis at an intercept, so we also need to test at 0 because that's where our x and y intercept is. You do not need to test based on where the oblique asymptote is. Remember, you could technically erase the middle of the oblique asymptote, and it's really here just to tell you that the end of this graph over here on the right should look like this line going towards infinity, and the end of this graph over here on the left should look like this line going towards negative infinity. Okay? So now I'm going to try and sketch what happens, and I'm going to highlight on here. Remember, the highlighting is not actually part of what you're doing, but I think it will help you understand a little bit why I'm sketching where I am, okay? So again, we know the ends, and then remember, as we approach this vertical asymptote, it splits our graph, but our graph doesn't just come to a halt. It tends to follow it. So I know that as I get close to this vertical asymptote on this left side, I'm either going up towards infinity or down towards negative infinity, and I know the same for the other side. So one of those things is going to be true. So I'm going to use these to try and help me along with this sine analysis. So when I'm doing sine analysis, remember, I'm essentially plugging things in to determine I have 5 times x squared over x plus 3. Does this turn out to be positive or negative? Does the point turn out to be above the x-axis or below? So let's say I plug in a number smaller than negative 3, like negative 10. Negative 10 squared would be positive times 5, so the numerator would be positive. Negative 10 plus 3 would be negative, so the denominator would be negative. A positive divided by a negative overall results in a negative. So I know, and this is where I'm going to highlight, so this is just a thinking process. You don't have to have this. This really isn't part of the graph. I just know that whatever I graph on this side of the asymptote needs to be graphed below the x-axis, because I only am going to get negative y values for every x I plug in there. Okay. So then I'm going to look at what happens between the other side of the asymptote and the x-intercept. So now I'm going to try and plug in something between negative 3 and 0. So let's say I plug in something like negative 1. What happens? Well, negative 1 squared is a positive, times 5 is a positive, so this is a positive, and negative 1 plus 3 is a positive, and a positive divided by a positive remains positive. So between the asymptote and the x-intercept, I would expect that every x you plug in results in a positive y, meaning you could only graph something above the x-axis. The last area I have to plug in is for numbers greater than 0, so I'm going to pick something like positive 10. I would get a positive in the numerator and a positive in the denominator and a positive overall. So again, that means anytime I plug in an x value that's greater than 0, I expect the y value to also be greater than 0, meaning I can only graph above the x-axis. So I'm going to try and use the end behavior, the asymptotes, and the points that I know to guide where I should sketch this graph. So Notice at the ends, I know I want to follow this red arrow over here at the left. Notice where I'm highlighted down here. I know that I cannot be going up near this asymptote. I must be going down. So I'm going to sketch something that goes down by this asymptote but follows this other asymptote here. So I'm going to draw a little curve like this. Then notice when I get to the other side of the asymptote, I know that I would not be following it downward on the right side because the shading is all up here, so I must be following it upward. And I know I hit this point that's an intercept, so I'm going to connect those behaviors together. I know I have to go up, but I know I have to come hit this point. When it hits that point, apparently it does not cross through the axis, but turns around again and goes up towards infinity because that's where the yellow highlighting is. And I specifically want to go towards infinity according to the end behavior, this line here that we drew to guide us. So it would look something like this. And now when you write your domain and range for these, they might be different for some of us. The domain should be the same. Basically, it's all real numbers except for x cannot equal -3. So I told you guys I'm okay if you just write x cannot equal -3. For the range, it kind of depends on how you sketched it. We should all have 0 as the lowest point for this branch that's up above the axis. So we should have that y is greater than or equal to 0. But there's also another branch down here, and it kind of depends on how you sketched it. The way I sketched it, it seems to hit this maximum value that's about here, which would be 1, 2, 3, 4, 5, 6, 7, 8.5, -8.5. So my other branch would say that y is less than or equal to -8.5. But again, if your sketch was a little different, those might be a little bit different. All right, let's look at part D. So again, remember we're kind of focused on the same thing. Oops, sorry about that. So we are looking for asymptotes, intercepts, and holes. So the first thing I'm going to notice is that the numerator here is factorable. So before I just decide to divide and get my asymptote, I want to factor it. And this actually has a cool and unique situation that happens. When I factor it, a factor cancels. Oops, I wrote this wrong. Let me fix it here. So a factor cancels, that x plus 2 cancels out, and my function just becomes x minus 2. Now, this is super important because this is no longer a rational function. This is just a linear function. So when I come here about all these asymptotes, lines don't have asymptotes. So this doesn't have a vertical asymptote or a horizontal asymptote or an oblique asymptote. Because I canceled out a factor, it does have a hole. So remember how we find the hole? We look at the factor we canceled out. When would that factor have been equal to 0? That would have occurred at x equal to -2. Okay, so the hole is a point where the x value is equal to -2. What would the y value be that goes with it? You plug it into your new function. So your new function, once it was simplified, is this very simple linear function x minus 2. What do you get when you plug -2 into that function? We get -4. So we're going to have a hole at the point -2, -4. And then for x-intercepts and y-intercepts, we still find them how we normally would. The process is the same for any type of function. For an x-intercept, I make y equal to 0. And here I get an x of 2. So the x-intercept would be 2, 0. For the y-intercept, I make y equal to 0, or excuse me, x equal to 0, and I get that y is equal to -2. And now I'm going to use this stuff to put on the graph. Now remember, I really don't have to do a sign analysis or anything here because I know now this graph is linear, so I'm really just expecting to draw a line. I just have to be cognizant that that line's going to have a hole in it, okay? So where does my line go? I have enough information here to show you. There's an x-intercept at 2, 0, a y-intercept at 0, -2, and a hole at -2, -4. So I can see that that line would go like this. Okay. And then for my domain and range, again, our domain is based on restrictions. Those come from the holes and the vertical asymptotes. So in this case, x cannot equal -2. The range of any line with a slope is usually all real numbers because it goes infinitely upward and downward. That's true here, except for remember we've removed this one point. So as far as the y values go, our graph has hopped over the y value of -4. So y cannot equal -4. And when you're listing the range, notice here I just listed exactly what it could not equal. But in the previous problem, I listed two different inequalities. You should only list what it's not going to be equal to if you're just skipping one or two numbers. If you're skipping a whole area like you saw in between these two branches here, you should list two different inequalities, one that describes the first branch and one that describes the second branch. So hopefully that gives you some idea of how these look when you don't have horizontal asymptotes.